Hey guys, welcome to potential energy. So it's basically the sibling of kinetic energy. So if kinetic energy was an energy in motion, right, a mass in motion, potential energy is literally that. It's the potential for something to move because of some position. I'm going to jump back down here to the equation real quick. The equation is pretty simple. It's just mgh, where h is the height relative to some location. So up here, I'm going to draw this little sketch real quick. If here the ground is 0 level, right, that means the potential energy is at a minimum for 0 joules. I'm going to raise it a distance here, h, right? And from here to here, potential energy is now at a maximum, okay? So potential energy at the top versus potential at the bottom, it's all based on the height. And so if you see here, this blue object here, it is at a minimum. Here, it would be at a maximum. And this green one is somewhere in between, so it's got a little bit of potential energy and a little bit of kinetic energy. This is going to lead us into conservation a little bit later when we talk about that. All right. So once again, potential energy, you'll see it written P sub G, U sub G, but most of the time we'll just use potential energy equals mgh, where m is the mass in kilograms. G, we tend to use 9.8 meters per second squared. And h is going to be the height in meters. So just to make sure we have the units right. The other type of potential energy we use is elastic potential energy. And so we talk about the elastic potential energy in terms of its K value. So if we think about it, a slinky is a type of spring. It's going to have a very low K value, okay? Whereas like a car spring in your suspension is going to have a pretty high K value. And a K value is based on this. This is called Hooke's law. And it's the force of the spring is the K constant times the distance you stretch it. You'll see it written K times delta X. So it's the stretch that you're making of. So basically we have some kind of initial length minus some kind of final length is how we handle that. So let's do an example. So you have a stuntman attached to a bungee cord. So he has an unstretched length of 15 meters, jumps off a bridge from a height of 50. When he finally stops, we have a stretched length. And so what we have here is, here's our bridge. The unstretched length of the thing is 15 meters. And then we have an unstretched length. Oh, this should be 44.0 meters. So this is going to stretch a distance of 44.0 meters. So if we notice here, we have this distance, we have this delta X, and we'll call it 44 minus 15. So the delta X value here, so 44 minus 15, is 29 meters. So that's the stretch of this rubber band here, okay? What we do know also is that the bridge itself is 50 meters above the water, okay? So it's 50 meters here. So there's a little bit of extra energy that we're gonna talk about first. But we're going to do the the potential energy of the spring. So it is 1/2 kx squared. So 1/2, it looks like my K value is 71.8. My delta X is 29 squared. So the potential energy in the spring is 0.5 times 71.8 times 29 squared. So we should get about a potential energy value of 30,191 or 192, rounding up a little bit, joules worth of energy from the spring right there. Well, if we remember, there's still some kind of distance here, and it looks like there's 6 meters left over. And so the potential energy at this point, potential energy is mgh. Well, we know the mass of the stuntman, 70 kilograms. Our gravitational pull is 9.8, and a distance of 6 meters above the ground. So if we crunch these numbers together, we get a potential energy at this point of 4116 joules. So the question's asking me, what is the total potential energy relative to the ground? We're going to get the potential energy, so potential energy total equals the potential energy of the spring plus the potential energy gravitationally where he is above the thing. So we just plug these numbers in, 3192 plus 4116. So we should get about 34,308 joules, or about 3.43 times 10 to the 4th joules, depending on how you work on it, right? All right, so potential energy is generally a little easier just because of the way the numbers are set up. The things that we will have to kind of be worried about is this K value for a spring, and we'll talk a little bit more about that in class. All right, guys, let me know if you have any questions. Thanks, bye.